You all, this is Darrell Lee Berry Jr. back with some more Science Hour. And looking at everything, it seems like the audio and everything is fine. Trying a slightly different setup. I tested it a bit ago and it seems to be fine, even though I think there's still a lag that I haven't really looked much into yet. So if you all know how to fix a lag, let me know. But I noticed that my voice seems to be slightly behind my uh, the video sometimes. I made a few other adjustments as well. You can see the coloring on the font in the chat and the size of the chat. I hope that makes things clearer. And as the uh, uh, cover image and title shows, we're talking about some thermodynamics today, something I was doing on my homework earlier. And it tied into something we were discussing last week. So I figured this would be a good topic to discuss and reinforce for myself as well. And so we'll talk about thermodynamics as far as engines, heat engines. And heat engines are basically um, power plants. A power plant is a heat engine. Um, Cars are technically, like automobile engines are technically heat engines, and the steam engine on the boats, like those old steam engines, all of those things are heat engines. And also refrigerators. We'll talk about refrigerators and we'll do some math today. We'll do some of the derivations uh, of how we understand and calculate the efficiencies of these engines. And it goes into how power plants work and things like that. I might even do one of those problems later, depending on how it goes. And those who show up, let me know how the audio is doing. It looks okay on my end. But let me know if I should adjust something. And we'll go ahead and get started. So I'll do a preface with a little bit of the laws, the first and second law. So we're talking thermodynamics, heat engines, refrigerators, right? So first law, which is shown on the screen there with this book. This is the book we're using in my thermodynamics class right now. An intro to thermal physics, if I recall the name. Increase the size of it a bit. And I think it's a pretty good book as far as books go. Lots of good illustrations, lots of good explanations. Right now, we're getting into chapter 5. If I recall, the book has 6 chapters. And right now, we're in chapter 5. And even though I can't even remember off the top of my head what the topics of chapter 5 are, we just started it. I was doing the homework earlier for one of the problems. Probably because I forgot. That's because I switched and started doing relativity homework. I'm starting to mix up my relativity and thermodynamic stuff. But I spent so much time doing relativity earlier. But thermodynamics, we're on chapter 5. This problem is from that chapter and is basically is dealing with refrigerators and heat engines and how they work. Now, the reason why I'm in chapter 1 is because the first law of thermodynamics is very relevant when it comes to heat engines, as well as the second law. So the understandings of these two laws goes into uh, making these various technologies that I mentioned earlier and improving their efficiency so that we have enough power to power our computers and cameras and everything else. So the first law is basically what I would consider a law of conservation. So it says that the change in energy is going to be the sum of the change in heat and the work that's input. So Q is a term commonly used for heat in thermodynamics, and W is a term commonly used for work throughout physics. And as we can see in the image that's in the screen right there, basically what's going on is you have a box with an opening at the bottom where a flame is contributing heat. And to the right, you have a piston. So that's a piston on the right that's pushing in. So there's work being done on the air to push the air in. And the combination of the heat entering from the flame and the work from the piston pushing it is going to result in a change in energy of the gas within that container. So for instance, since heat is going in through energy and work, it'll start to speed up. It'll have more energy. It'll have more entropy, since there will be more ways for the uh, uh, molecules to arrange themselves with the increased energy. So that's basically the first law in a nutshell. The second law, which we spoke about before, and I'll see if I can find the equation really fast. As far as the book, so it could be on the screen, could just write it down, but it's good having the reference there. So the omega there is referring to the multiplicity. So think about the second law. You see how it's talking about large systems. The second law is basically referring to um, systems that are large enough to where it becomes probabilistically uh, relevant to like not talk about the individual particles. And so that's that. And here we're getting to uh, the law right here as far as the log of the multiplicity. So technically that's the law without the the Boltzmann constant included. So that gives you basically a unit. So it's basically entropy divided by that constant. And what happens is we end up multiplying the log by K. And that's what gives us the entropy equation proper, which is what we get to here. So basically we have the S equals the Boltzmann constant. I'll put a mini b times the logarithm, the natural log of the entropy of the system. So basically S is entropy, KB is the Boltzmann constant, and omega refers to the multiplicity of the system, um, the number of ways that the microstates can arrange themselves in the system. So the greater the multiplicity, the greater the entropy will be. So the more ways that the molecules can arrange themselves, the more of this stuff that we call entropy will be there. This this order that the universe is tending towards in the larger sense. So you can have a process that in itself the entropy stays the same or lowers, but the overall entropy of the system has to increase. Or basically, let's just say the overall entropy of the universe has to increase overall, which is to say the um, the multiplicity of a system is going to tend towards the state that has the most microstates. So that's basically the law of entropy in a nutshell, that it goes towards greater entropy. Right? And I see somebody showed up. Let me know if you have any questions, and I can clarify anything. But this is sort of the preface background So we will discuss in a bit. And another thing I'll input here is the change in entropy. Well, actually, we'll get to that part. And I can actually turn off the book momentarily. And I'll move this over a bit. And before I go, by the way, before I go into the topic, let's look at the background a little bit. So the background that I have here behind me are actually cooling towers at a power plant. So this will directly relate to what's going on as far as how a heat engine works, which is means, how power plants work, how technically a car engine works if you consider the heat that's coming from the burning of the fuel as if that's heat coming from the outside and the way that process works. Um, and technically, I guess a heater. I mean, if you basically it works the same way as far as where we place the dumping of the heat at. So what I'll do first, I'll start with an engine. Let me update the text, by the way. I'll see if I can get in the habit of updating the uh, leading text up there about what we're discussing at the moment. So now we're on two heat engines. So if I was to draw a basic schematic of a heat engine, basically, so this would be our engine here. Let me switch it back to the sheet I'm drawing. And the way a heat engine works is it basically takes temperature or heat from some heat reservoir. So we'll call this our heat reservoir, where there's a whole bunch of heat that we can draw energy from. And it takes heat from this heat reservoir, the engine does. And the way the heat engine works is it wants to take this heat and convert this heat into work. So, for instance, if we're talking about a power plant with these large turbines, let's say a nuclear power plant, it's using the nuclear fuel to heat up the steam, and the steam is carrying the heat into the turbines into the engine. So the heat goes into the engine, it turns the turbines, and the turning of the turbines has a series of magnets and things up in there. Well, I was a learning assistant for an electricity and magnetism class in the fall, and the professor actually went into a little bit of detail in this and showed some images of how there's these magnets around the turbines and when they turn, how it uses a power plant uses so many different laws of electricity and magnetism to do what it does. But the turbines turn and it takes this heat and it outputs work. So it's outputting work that we can utilize to make electricity and power things. And it also, in the process, dumps some heat. So it needs to have some place that's cool to dump heat into. So we'll call this our cool reservoir, our cold reservoir. So in the image in the background, the cold reservoir is the air. It's basically taking the heat from the steam, turning or working through the engine. Some of that uh, heat energy goes into work that we use to power everything, and some of it is dumped into the atmosphere, which will be our cold reservoir through those towers there, those cooling towers. And so basically this heat here, QH, and this Q here, we call it QC. and the benefit of our process is the work. So the work is the benefit that we gain so that we can turn that work into electricity or whatever you want to do, or turn that work into moving a car down the street so we can get to where we're going. We're turning it into some kind of work so that we can utilize it and make things happen. So where the first law of thermodynamics comes in is we see that the change in energy is the heat plus the work. And the same dynamics works here, where in this case, the heat energy here is going to equal the work that goes out and the energy that goes out into the cold reservoir. So as we can see, whatever QH is, that's going to be the limit on the work we can do and the heat that we dump into the cold reservoir. So however much Q that is, some of it is going to go into work, some of it is going to go into temperature, into the cold reservoir, like in the towers in the image. And there's a certain efficiency that goes with this. Like, only so much heat is going to be transferred into so much work. Some work is going to be lost in along the way. But we can pretty much uh, codify that the benefit is the work and the cost is the heat that's coming from outside. So we define this parameter, the E, I forget the actual formal name for it. We'll just call it the efficiency, or it might be efficiency, but I thought there was some kind of different formal name. So the efficiency is going to be the work that we gain divided by the heat. So basically, if the engine was 100% efficient, then we'll take in a certain amount of heat, we'll output the same amount of work, and it'll be 1. So 1 will be the most efficient it can be. Uh, and of course, it's going to be less than that because not all heat is transferred. So what we can do is we can make this into a simpler form utilizing the first law, because we can see that from the first law, if we was to rewrite this, we can see that work equals the heat from the hot reservoir minus the heat that's being dumped into the cold reservoir. So we can say E equals work over QH. That's simply rewriting the efficiency. And plugging in what we have for work is going to be QH minus QC over QH. And then we can simplify this to be QH over QH minus QC over QC. So we can say that E, or the efficiency, is going to be 1 minus, it should be a H, 1 minus QC over QH. So this is going to be the efficiency of a heat engine, which is going to be determined by in terms of energy, the energy that's coming in from the heat reservoir and the energy that's going outward into the cold reservoir. So again, if no heat goes out into the cold reservoir, meaning 100% of the heat is converted into work, then QC will be 0, and thus we have our 1 efficiency. So we can see how we still have a 1 efficiency, whether it be with this equation here, where 100% of the work, 100% of the heat is turned into 100% work, and thus E equals 1. Or we can put it in terms of 100% of the heat goes into work, so 0% of the heat goes into dumping into the cold reservoir. So that term equals 0 because QC equals 0, and then the efficiency is still 1. Now, another way that this uh, relates to the second law is that with this heat, as we discussed earlier, comes entropy. So along with this heat, entropy is coming as well. because with more energy, the particles have more ways to arrange themselves amongst each other, and thus the entropy goes up. So because the if you have a state is going to tend towards the state with the highest multiplicity, the macro state with the highest multiplicity, that means that entropy tends to increase. This means that this whole system, the entropy in the end has to be either equal to or greater than the entropy at the start. So if you think about this heat engine or any engine, you notice that it turns over as cyclical. So basically the heat comes from the outside, it goes around, and then the whole process starts again. It's like with our engine, we can hear it turning over and over and over again, going through that same cycle over and over and over again, which means that when this engine goes through one cycle, it has to reset and go back to where it was. So the entropy has to somehow either be the same or be more. So the second law of thermodynamics is satisfied. Basically, we can't make an engine more efficient than that, at least yet, because we find some new physics. But at this point, we're limited by the fact that the entropy is going to be either the same or greater, and it's going to limit the efficiency of how efficient this heat engine can work, because so much heat is going to have to be dumped out in order to make sure that the entropy of the entire system either increases or stays the same. So the way that this can be written is the change in entropy is going to be the heat, is the energy over the temperature. The heat energy over the temperature is going to be the change in entropy for any system. Hey, what's going on, the mathematician? I'm doing good. How have you been? Good to see you. Doing some thermodynamics today. And let me know if I sound okay, if everything is looking fine. And all right, so we know that entropy, this is another way to look at entropy. So basically if you add a lot of energy to a system, but the temperature stays the same, let's say we have a uh, a container here, and we have some air in the container, and we add some fuel, but the temperature doesn't increase. Awesome. Thanks for letting me know everything is fine. Hey, what's going on, Catherine? Thanks, Catherine. Appreciate it. Yes, please like, please subscribe if you haven't, and help me get to 1,000 subscribers. That's the next goal. I hit 300, so the next goal is 1,000. So let's say we have some air, we're adding some heat. Let's say we want the temperature to remain the same. So the only way the temperature can remain the same is if the volume increases. So the volume increases so that the faster moving air can spread out. So if the Q goes up, but the temperature stays the same, we can see that the entropy has to go up. So one of my physics professors, one of my favorite physics professors, as a matter of fact, in which physics class was that actually? That was EM course. Thinking about it, ironically, he was a great professor. And he used to do this sort of using the equations and drawing arrows to demonstrate. So if Q goes up and T stays the same, so we have an arrow going up here and an arrow going horizontal here. In order for if this happens, then we know that the entropy has to go up. And she did actually, the mathematician. If you go back to the previous video, he made a comment. So if you look at the previous video, she made a comment in the chat, and she put the solution there. And I thank you for reminding me of that. I wanted to highlight that actually. So remind me at the end, and I'll bring that chat up, and we could take a look at it. You're welcome, mathematician. Just remind me at the end, and I'll pull it up, and we could take a look at her solution. So we have that. Um, Similarly, if the temperature goes down, but the energy stays the same, we can say the entropy goes up as well. But here we're just talking about the heat because we see that we're pulling heat into the engine with the engine is pulling heat in, so we know that the energy is changing. So we can say that we have some entropy for the hot side. So the hot side of the system here is putting some entropy into the engine. So it's going to lose some entropy. So the Q here and T here, so we know that the Q is going down because we're pulling some heat from the outside. So we'll call this QH and TH. And we have the entropy from the cold side, because again, the heat is going to be dumped into the cold reservoir. In the image, we can see the heat being dumped into the atmosphere. The air next to the atmosphere, next to the cooling towers heats up. There's more ways for the air molecules to now arrange themselves. So now they have more entropy. So we can see that there's a change in entropy on the cold side in the cold reservoir. Okay. Now, but keep in mind that according to the second law of thermodynamics, the entropy has to either stay the same or go up. So what this means is that the entropy of the whole reservoir has to be greater than or equal to the entropy of the hot side. Right? So basically, this is the start of the process where it pulls heat from the outside. The engine does its work, and then it dumps the heat out here. So basically, we know that by the time we get to this step 3 here, the entropy of the entire system has to either be the same or increase. So the entropy of the cold side has to be more or equal to the hot side. So if we were to plug this in, we can say that QC over TC is greater than or equal to QH over TH. And if we were to solve for this to put this in the same terms, we could say QC over QH is greater than or equal to QH over, did I mix it? Oh, TC over TH. So we have this. Now we're getting closer to the simplification as far as the simplification of the efficiency in terms of the temperature of the system. So I'll bring back the efficiency equation and write it over here. We have 1 minus QC over QH. And the way I learned to think about this is you can see we have QC over QH in both of these places. Listen, Catherine, I'm glad you enjoy. And keep in mind that this stuff is, we don't realize it, but we use this every day. Every time we turn on the power on our wall that's connected to a circuit that's connected to some high voltage cables that's somewhere down the line connected to a power plant. And these equations went into determining the efficiency of that power plant. How much energy we could extract from how much heat, how much nuclear fuel we need, therefore how much they can charge, how much profit they can make, and so on and so forth, how much we end up paying. So these equations are relevant, even though, unless we work at building power plants, we might not actually use them on a regular basis, even though, like in the book we were looking at earlier, something as simple as heating up a certain area. Oh, I forgot I turned from that page, but if you scroll back earlier, it had that little image with the flame. It's applicable in several places. So what I'll do is I'll write this equation here again, and we know that QC over QH has to be greater than or equal to TH over TC. Now, I'm going to copy this down, and I actually have to think a bit about this correlation. So I'm thinking about it again to make sure I explain it well. QC over QH has to be greater than or equal to TC over TH. Will obey the laws of thermodynamics. That's this part right here. And if we was to write E in both of these forms, what that will mean is if I take E equals 1 over 1 minus QC over QH, and I have E equals 1 minus TC over TH, Since QC is going to be bigger, that means since QC is bigger, if I subtract 1 from that, this side is going to be smaller. You see that? Because if PC is smaller, then I subtract that thing, this right side is going to be bigger. That's the only way I think about it. So let me go through that again. What I did was, we see that these two are related. QC over QH, the energy that we dump into the outside, like in the towers, the energy that we're dumping outside into the towers, divided by the energy we're pulling in from the steam from the nuclear fuel, that ratio is going to have to be greater than or equal to the temperature outside divided by the temperature of the steam that we're pulling in. If I plug these both into the efficiency equation, that means that since this term is bigger, it's going to result in an overall smaller E than this term over here, since the TC over TH is smaller, right? So if I erase these E's, we see that 1 minus QC over QH is going to be smaller than 1 minus TC over TH, right? So that means that E, because remember this is E is going to be less than or equal to 1 minus TC over TH. And this is basically the equations that, TC over TH. So for instance, when a investor or somebody is building a power plant, this is what they have to look at to determine the efficiency of that power plant. For instance, if we're, in California and the temperature is 100 degrees outside, what temperature do we need to get the steam to have a high enough efficiency to where we can lower the price of our electricity by this much? So that's going to determine how much fuel we need, how much nuclear fuel we need, how much we need to heat the steam. Do we need to heat it to 500 degrees Celsius? Do we need to heat it to 600 degrees Celsius? What difference in temperature do we need to get the efficiency that we need of that engine so that we can produce the power that we want in an efficient enough way so we can keep the price at a certain amount, or so we can charge so much profit, whatever the case is, right? So this is the efficiency in terms of the temperature of, again, the cold reservoir, which is where we dump in the heat, and the heat reservoir where we get in the heat from. As far as our power plant is going to be the steam from the nuclear fuel. As far as the engine in our car is going to be the gas, the heat from the gas that we burn. If we just imagine that we burn that gas, we get that heat, and the heat, just imagine that heat just coming from a reservoir, and so on and so forth. So let me know what questions you all have, and I'll see if I can answer some questions on the heat engine before we move to a refrigerator. Let me know what comes to mind. And I'll let some time go on for some questions in the uh, on this while I start drawing a refrigerator engine. Delta S. So delta S is change in entropy. So this is change in entropy. So this is basically a measure of, um, so basically if you have a system, let's say you have, in this case, we're talking about a system of uh, hot energy here, high energy here, and low energy here. And let's say inside that reservoir, let's say inside of the power plant, when they heat in the steam, that the energy, that those air molecules are moving around really fast. So there's a lot of different ways they can arrange themselves. So that means that system, just looking at the heat energy, the heat reservoir, has a lot of entropy. It has a lot of different ways it can arrange itself, and it's arranged in such a way to where uh, uh, the most things likely that can go on are going on. So for instance, all the molecules won't be like stacked. on this side of the, container that's holding the steam, it'll be distributed in such a way to where it occupies as much space as possible. And the cold reservoir, which is outside, the the energy is going a whole lot slower overall. But the thing is, since the energy is going slower, when I dump energy from the hot reservoir to the cold reservoir, since the molecules here are going slower, it doesn't take that much energy to make it go faster. Like if you think about it, if you have something that's really cold and you put some heat in it, it could warm up really fast. But if you have something that's already hot, it takes more energy to get that thing hotter because it's already hot. You know, if something is already cold, like if you have ice, you can see it melt really fast. But if you have water sitting there, it's not going to just start boiling spontaneously. It takes a lot more heat to get it moving. So what that means is in this process, when the energy goes from the hot reservoir to the cold reservoir, since the cold reservoir can move around a whole lot more with less energy, its ability to take on different positions is much greater, so the entropy increases. And what entropy says is that the overall change in entropy, when the entropy here goes down because it's losing heat, and the entropy here goes up because it's gaining heat, overall, the ways that things can arrange themselves overall is going to have to be the same or more. Right? Now, the fact that things that are cold can move around a whole lot more with less energy than things that are hot, that's how we can extract some of this energy as work. Right? So even though this heat reservoir loses this much energy, it takes less energy to heat this up to get the same amount of entropy than this thing lost. And that difference goes out in work. Right. So hopefully that was clear and basically relating entropy to the work and the heat change that's going on there. But that's what that's talking about. Whenever you see S, at least in physics, that's usually talking about entropy, that the ways that things can arrange themselves and how the universe wants to tend towards the situations where things are most dispersed, when there's most activity going on. Does that seem clear in the mathematician? Awesome. Is okay, got you. And Catherine says, do you specifically decide on areas to build power plants for better entropy, maximum efficiency, involving outside temperature, average wind speeds, etc.? Awesome. I'm glad it's clear, mathematician. I can't say for sure, but I don't think so. I haven't heard that said before because the thing is, the temperatures that they go up to, like for instance, one of the things we have to calculate in my thermodynamics class, he gave us an example of a power plant that is heating water to 500 degrees Celsius, and we have to calculate the efficiency change if the piping and everything inside the power plant was built to be more efficient, and they was able to get the steam to 600%, to the 600 degrees Celsius. So, you know, if you're looking at a temperature that's 100 degrees outside, I can't really say it's going to be a big difference from 50 degrees as far as a difference. So, we have 50 to 550, that's 450 degrees, and 50 to 650, that's 550 degrees. Um, is that a big difference? I don't know. I don't know if that's so. I don't know if they really do that. It seems to me that they just make more efforts to make the difference bigger, but I could be wrong about that. Right. Another thing we have to keep in mind as well, Catherine, is that we have to send the power. So in my EM class that I was a learning assistant for, my professor was really good about this. He actually did a calculation about about high voltage wires and why it has to be high voltage wires. And he basically did a calculation. We didn't have to do this. I was helping the students in the class. So I would like spend more time learning things that I would have to cover with them as far as homework and stuff. But this is just something he did as an aside to show how this works, like why our power wires are high voltage. So basically, he did something with a low voltage power wire, and he showed that the amount of electricity that can go through is much less than if we have a high voltage wire, right? So let's say we decided to build all our power plants in Antarctica. We would have to send that electricity from Antarctica to wherever we're going to send it at. So then we have to bring into how efficient the wires carry the electricity. So when you take all of these things into account, it's probably just easier just to build a power plant where you're going to get the electricity at as close as possible, and that temperature difference is not going to make a big difference, right? So basically, what we're going to have to look at is whether TC versus TH is going to make a big enough difference of the transport of the power from where we're making it to where it's going to be. So this stuff starts to get pretty complicated. When you start to really learn what's going on, you start to appreciate science and appreciate the effort and the know-how and the expertise that goes into just being able to flip on a light bulb. The expertise behind this stuff and building these power plants and getting that power from there to here, there's so much that goes into it. So hopefully that answers your question, Catherine. And ABCD says, hi, mathematician said about the channel. He said, it's the best channel to learn math. Awesome. Thanks, mathematician. I appreciate you passing the word. So thanks for letting them know. Uh, 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 Tell you what, hang around for a little bit, ABCD. If I see you a few times and you seem pretty chill, I will make you a moderator as well. So eventually we'll get to the point where we'll have enough people here to where moderators actually start doing things. So as time goes on, I'll be less and less fluent with giving out moderator. But if I see you around a bit, especially since you're a friend of mathematician, so a friend of mathematician and you hang around a bit, I'll make you a moderator as well. Give me a week or two. Ah, thanks. Awesome. Yeah, he's the professors are all of these people are they're legit. So they're so experts in what they do. Awesome mathematician, but keep on hanging around, I'll make you one as well. So let's go to refrigerators. So refrigerators are actually very similar to our power plant. So basically for one of my homework assignments, by the way, I had to actually this derivation was pretty much given to us in the book. The refrigerator one was given to us in a bit, but not all the steps were filled out, sort of. And one of the homework problems we had to do was do this derivation to get the efficiency of a refrigerator in terms of the temperature of the two reservoirs. So for instance, if we're looking at a refrigerator, right? So this is our fridge. This is going to be our cold reservoir, because that's where we want to send the cold into. And the hot reservoir is going to be the room. Basically, the room around us. Basically, what's going on is the engine is basically pulling energy from the refrigerator and dumping it into the room around us. So in this case, the engine has to do the reverse. It has to pull heat from something that's already cold and dump it to something that's already hot, basically relatively hot. So if I was to draw this process, and I'll start this on the new page, I'll try to keep the uh, uh, same setup. So we have a fridge. And basically now what we have is we still have our heat reservoir, but now it's the room. And I'll still keep that red. But in this case, what we're doing is we're dumping energy, as we said earlier, into the heat reservoir. So we're taking energy out the fridge. At least the engine is taking energy out the cold reservoir and dumping it there. This is our cold reservoir, which is the refrigerator. And basically we're taking energy from the refrigerator with the engine. Oh, let me make this a bit more visible. And technically, I guess, well, I mean, this is all one thing, but maybe it'd be better if I actually call this the engine. I guess my erase thing is a bit too big. Let me make this thing a bit smaller. I must have mistakenly, yeah, I did. Maybe mistaken hit the giant erase thing. It's like erasing so many things. I'll still call this a, it's the best thing to call this. I mean, fridge is good enough. Just keep in mind that, we have the part that's actually the cold part, where we like freeze stuff at. And then we have the part that's the actual engine that's making this thing go on. Now, in this case, what happens is we actually have to do work to make this thing happen. So if we compare these two things, we'll see that this is basically the heat engine in reverse. Here, we have the engine. We're dumping work out. Basically, we're pulling heat in. We're dumping heat out. We'll be pulling work from that. Here, we're using work to pull energy from out the cold part and dump it into the heat part so we can make the cold part cooler. So now we have our QC, which is going this way. We have our QH, which is going that way. And earlier we had a benefit of work. Now we have the benefit is going to be the QC, meaning, of course, when we have our refrigerator, whether it be the room, we have our air conditioner that's cooling the room. The benefit is that we're cooling our house. And the cost is going to be here, the work. So the work that we put into this engine to draw that energy out of the cold, that's going to be the cost that we have to do this cooling that we have. So it's still the same thing, benefit divided by cost, and I'll call this cost of performance. So before, the cost was where did I put it? The cost was the heat. Basically, we have to use like nuclear fuel to heat up the steam, so it's going to cost, and that cost we're going to draw work from it. Now the cost is going to be the work. So I have to, put in some work to make something that's colder, and the benefit is going to be the fact that it gets to be cold. I get to enjoy my cold room and my cold ice that I put in my beverages and so on and so forth. The first law of thermodynamics still holds. So the same first law that we mentioned earlier, QH equals work plus QC. And as we can see, that's the case. We have our QH here, and we have the work going into it, the QC going into it. Both of those two things, the QC and the work, equals QH. Give me a moment, I'll see if we have any questions so far. Awesome, mathematician. Thanks. And I appreciate your referrals. So hopefully we keep on building. That's the plan. Then we have it. So then we have the way, and again, the actual process of a refrigerator gets very complicated, like if you have to actually build one, but this is what it's basically doing. We're using work to draw energy from something that's already cold, dump it into what's already hot, which is our room. So let's do the same thing that we did before. Let's find the efficiency in terms of temperature. So we have COP equals QC over W. And we can do the same thing and put work in terms of those two things. So if I was to take the first law and we work it, we have work equals QH minus QC. So work is going to be the energy that we dump into the hot minus the energy that we pull from the cold. So that's going to be the work. And we can see it clearly here. Is working to pull energy from the cold and dump it to the hot, right? Oh, and I think I reversed what's my Jenkins? Yeah, that was it. QH minus QC. So then we have QC over QH minus QC. Now this one gets a bit more complicated as far as the algebra. So if we look at this, and I'll try to break this down, I can actually multiply this by 1, and it stays the same. So again, we have the energy that's in our refrigerator already, divided by the energy that we're going to dump outside it minus the energy that's already in there, the work on the bottom. And what I'm going to do is I'm going to divide this by QC over QC. And I'm going to color code this so it's clear what I'm doing. So why don't let's color this orange. I'll keep the dividing line black, and I'll color this. Does that show up well? Gray. I'll color this. Um, oh, pink. There we go. So watch what I do here with these two numbers. Now, again, all I did was multiply by 1. You multiply by QC divided by QC is still 1. But watch how I distribute this. I'm going to divide the first QC by the pink QC. I can move these around however I want. And I can add another step here if you want me to. Just let me know if you want me to add another step. And I'm going to take the top QC. I'm going to divide by the things in the bottom. So it's going to be QC divided by that QC. Oh, and this is my H, my bad. So QH divided by that QC. And then it's going to be QC divided by that same QC. So basically, I took the one at the bottom, I brought it into the numerator. I took the one at the top, and I flipped it into the denominator. And I guess instead of adding another step, I could just write on the side right here, and I can say QC equals 1 over 1 divided by QC. Just like how 2 equals 1 divided by 1 divided by 2. We know that 1 divided by 1/2 is 2. So this is the algebra behind this step that's allowing for this simplification. So that means we have QC divided by QC in the numerator. That's going to equal 1. We still have QH divided by QC over here. And then we have QC divided by QC right there, and that's going to equal 1. So we have the coefficient of performance of the cooling device is going to be COP, is going to be 1 divided by QH divided by QC minus 1. So this is an equation of the efficiency of a refrigerator in terms of the energy that's being moved around. And I'll do the same thing and put this in terms of the temperature, which is what we had to ultimately do for the homework assignment. So let me stop and see if there's any questions at this point. So if you have any questions of what we did so far, let me know, and I'll keep going and I'll take a look at any questions that come up. So again, the same thing has to happen here. So in this case, as far as the entropy, I'm pulling entropy from something that's cold. I'm dumping it into something that's already hot. So as we discussed before, the amount of energy that we dump is going to have less effect on what's already hot than the cold. And the entropy overall still has to either be the same or increase. That's the limit on the efficiency of our machines, right? The entropy has to either stay the same or increase. The machines just won't work otherwise. Otherwise, we would already have a free energy machine. If we can make things work such that entropy doesn't increase, then we can draw more energy than we put in. Since we can't do that, the entropy on each of these sides has to either be the same or increase. So what we have here is that the entropy this time on the hot side is going to have to be greater than or equal to the entropy on the cold side. But again, here we're taking energy from here. This is the first step. The energy does some work, and then we dump it out here. So since this is the in part, the entropy hot has to be greater than or equal to the entropy cold. So that's why I have this like this. Entropy hot has to be greater than the entropy cold. And we know from earlier that entropy hot is going to be QH over TH. And entropy cold is going to be QC over TC. We know that's going to have to hold. And we could do the same thing and move these things around and say QH over QC is going to have to be greater than or equal to TH over TC. Right? So this is the relationship relating the temperature of the hot and the cold of a refrigerator relative to the energy that's being moved around in a refrigerator. And now we can start to relate the efficiency of a refrigerator compared to how hot or cold the environment is. Right? So let's look at this. Let's see what we have. So COP, I was going to bring that down again. We have our COP is, and one thing I'll mention, by the way, this is actually the Carnot efficiency. Like this is the maximum efficiency of an engine. This E here is going to be the maximum efficiency. And the same thing here, this is going to be the maximum efficiency of whatever it is we're working with. And now we're going to see what the limits is going to be based upon, jumping ahead of myself, energy, QH over QC minus 1. So I need to think about this again because again, I had to think about this myself earlier. So let's look at this. So QH over QC has to be greater than or equal to TH over TC. Let's go ahead and write both of these. I'm going to write 1 over QH over QC minus 1. And on this side, we have 1 over TH over TC minus 1. So if QH is going to be bigger, right? If QH is going to be bigger, then when I subtract 1, so let's actually extract this. I'm going to write this in a different color. QH over QC is going to be bigger minus 1. And we have TH over TC minus 1. So if QH over QC is bigger, let's subtract a number, this is going to be bigger. So if QH over QC is bigger, this number in the denominator is going to be bigger, and this number in the denominator is bigger, this is going to be smaller. So if I have 1 divided by 4, that's going to be smaller than 1 divided by 3. So if TH over TC can be smaller, this smaller number minus 1 is going to end up being a smaller number. This whole thing is going to be smaller, so this is going to be small. So this is going to be bigger. So 1 divided by 3 is bigger than 1 divided by 4. You see what that is? So that means that since COP is this, that means that COP is going to be less than or equal to 1 divided by TH over TC minus 1. So that means that the efficiency of a refrigerator in terms of temperature is going to have this relationship. So let's look at this and see what this will tell us. This means that if, let's say, the refrigerator, the inside of the refrigerator, is the same temperature of the room. So let's say if pH equals TC, this means that COP is going to be 1 divided by T over T minus 1. So it's going to be 1 divided by 1 minus 1. So it's going to be infinity, because the 1 divided by 0 is infinity. So that means at the same temperature, that thing is going to be extremely efficient because it don't have to do any work, which is why it turns off, right? So if you set the room temperature to 50 degrees, for instance, and you set your refrigerator to 50 degrees and you open the door, what's going to happen? The refrigerator is going to be off. It's going to stay off because everything is 50 degrees. So that means it's perfectly efficient because it don't have to do anything. By the same token, if you have, let's say, if the temperature of the outside is, let's say, it's very hot, very different. So TH, let's say, is way bigger than TC. So the COP will be 1 over let's say it's 1,000 times bigger. 1,000 minus 1. So this is going to be 1 over some, 999. So the efficiency is going to be very small. So the bigger the difference in temperature, the less efficient it's going to be. So if you think about it, if you have a refrigerator and it's, 1 degree in here, but it's 1,000 degrees out here, it's going to take a lot of work to make this hotter. It's going to take a lot of work to make this 1,000 degree thing out here hotter. So the thing is going to have to work really hard. So it's going to be very inefficient. It's going to take a whole lot of energy to keep that refrigerator cold in a 1,000 degree room, which makes sense, right? If you have a refrigerator in a room that's 1,000 degrees, so you have 1,000 degrees trying to heat that refrigerator, it's going to be very hard to keep that thing cold in that 1,000 degree room. So it's going to have to work very hard. It's going to be very inefficient. So we can see how this equation works with our intuition. And again, these are the equations that people use when they're building a refrigerator and they're trying to get this efficiency. We need to design this thing so that in the average room temperature of 70 degrees or whatever, this thing will work efficiently, right? So they have to work its components, do whatever they got to do to make sure that, in a room it works efficient. And right, when they put on the refrigerator, this thing is this efficient, is going to cost this many wattages. That's how they know that, because they can use these equations and say, okay, the room is going to be this hot on average. We're going to put this engine in it. What type of engine can we put in there where it's going to be this efficient? We're going to need this much electricity, so we know we're going to need this much wattage to keep this thing working. And then they can put that stamp on your refrigerator saying, this is how efficient this thing is. This is how much power you're going to need to work this thing to keep your temperature at this. Right? This is how all this stuff is done. Um and uh and the mathematician says, do you know how to calculate the lower efficiency? You could just plug in whatever temperatures you want. So let's say, well, that's a good point. Yeah. So I guess the lowest efficiency would be the maximum difference in temperature. So if your house gets at the most 80 degrees Celsius, and you want your refrigerator to be 20 degrees Celsius, then you'll be able to get the lower window of your efficiency. And you could either increase your temperature of your fridge, or you can lower the temperature of the room to adjust that. So good question, mathematician. So you could just plug in those numbers into this efficiency, and you can determine what's going to be the lower ceiling of your efficiency depending on your room. So I chose a pretty extreme example to try to, you know, uh, illustrate the point. Um, but let's say your room is 80 and the fridge you want it to be 20. We know it'll be COP equals 1 over 80 minus 20 minus 1. So there's going to be 1 over 4 minus 1. So there's going to be 1 over 3. So you're going to have efficiency of about 30%. It's going to be about the efficiency of, I guess I should say 33%. Right. So if you have a room at 80 degrees Celsius, a fridge at 20 degrees Celsius, that'll be about your efficiency. Normally this stuff is in Kelvin though, so I probably should do it in Kelvin, but you get the picture. And mathematician says, do you subtract 100? We're just basically plugging that into the equation. So let me make sure I didn't make a mistake here. Mm, 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 mm. I guess it's more accurate to say if the temperature was 1,000 times more. If that's what you meant right here. So if the temperature inside the room was 1,000 degrees and you wanted the temperature inside to be 100, like if you had 1,100, and that would work if that's what you meant. And then I just plug this into here and got that calculation there. And Catherine says, does this mean in a room between 0 and 5 degrees, say on the cold night, you could potentially leave the door open of your fridge? Sure. If you want it to be that degree, sure. You should try it. And we know that's the case because we can listen to our refrigerator. We know that if, once it gets to a certain temperature, it turns off, right? And as long as you keep it closed, it's insulated so that it can more easily maintain that temperature. And then once the temperature rises to a certain point, it heats up. The same thing with our thermometer, right? We have our thermometer on our wall, and it has a little dial, whether it's a dial like this or a digital dial, and it tells us the temperature. And let's say we turn it down. Let's say we turn our dial down to right now it's 75 degrees, right? And we want it to be 72 degrees. So I turn my dial down to 72. So the dial says 72, but the thermometer still says 75. And what happens when it gets down to 72, the thing turns off, right? So if your refrigerator is the same temperature as your room, yeah, it'll turn off. You should try it because we see it all the time. Air conditioner is nothing but a refrigerator. The air conditioner is nothing but a big refrigerator. So in our room, the fridge is the box, and this is the cold reservoir, right? So remember, this is our cold reservoir, and the room is the hot reservoir. But for the air conditioner, for the AC, the house is the cold reservoir, and the universe, which is really the planet, is the hot reservoir, which is outside. And we know that when when it's cool outside, and we turn our thermostat up because it's cool, it turns off. We open the door and never turns on because the temperatures are the same. So that's exactly right. Awesome. So that's all I have for today, you all. So now you all see how these calculations are done to get the efficiencies of power plants, refrigerators, and this is a little bit of the background of how that works, of people who really understand thermodynamics, which is the people who build refrigerators and power plants and so on and so forth, and know what it really has to deal with. And let me pull up, by the way, that example that Catherine so graciously put for us, and I'll pull that up and I'll do a screen share of that explanation. And we could take a look at that, the problem that she solved for the mathematician last week. I'll share that on the screen so we can take a look at that solution. So it's on this video, by the way. Let me put the link in the chat. Share copy. Boom. And if you look in the comments, share this screen, you'll see the solution there. Now go ahead and share it on the screen. What's the best way to share it? Probably best to just put an image up. Let me see here. And I pinned it to make it easy to see as well. So add image. So this is, oh, and the thing is playing. Hold on, let me cut it off. Awesome, there you go. That's the solution there that she worked out for us. So thank you for that, Kat. We appreciate it. And that's the solution to the problem that the mathematician brought up last week. So if you go to last week's stream, you'll be able to see a problem that I shared on the screen for mathematician. And there's the working out from Catherine. And there you go. And she's there in a chat, mathematician. If you have some questions, you can ask. She says K nominated category four, category for 3 points, for category 2 history for 2 points. And the question started with that equation. And those are the working with a few steps skipped to give you that solution. So thank you for sharing that, Catherine. We appreciate it. So awesome. Thanks everybody for showing up. Pleasure talking to y'all. Pleasure seeing y'all. Let me know if you have any thing you'd like me to cover future weeks. As a refresher, right now I'm doing relativity, thermodynamics. I'm building scientific apparatus, and my other class is quantum two. So we haven't done quantum two in a while, so maybe I'll talk about quantum two next week. Quantum mechanics gets, I mean, it's so amazing learning about all the intricacies behind. Like we talked about the intricacies of power. We have to think about the wires and so many things go into just being able to turn on the light. We just flip a switch, right? But there's so many things that goes on behind it. So then when you talk about quantum mechanics, um, there's so many things that goes on in quantum mechanics just in making bonds with things, right? Like when we take our medicine for instance, you know, people made these chemical compounds from making bonds, and there's a lot of quantum mechanics behind why two things bond. How much energy does it take to bond them? How much energy will it take to break them apart to make a new bond? Um, you know, how much energy would it take to break it apart so that we can use that energy as electrical energy? That goes into making batteries. Because it just made me think about the connection with thermodynamics. It's amazing all the things that goes behind the scenes. So maybe next week I'll talk about some quantum mechanics, a little bit of how are quantum mechanics are seen in quantum two. But again, that's not set in stone. So if somebody else comes up with another idea, just make a comment on this video, make a comment in the little post thing that they have on YouTube that you can make a comment there and reply. I already set up a post for that last week. And I'll see you all next week, same time, same station. Have a good evening. Oh, one more thing, mathematician says explain. Let's see if this one more explanation comes up. Oh, mathematician says, do you believe in aliens, but why do you have any evidence? Uh, uh, just from the fact that there's so many galaxies. Like if you look in one of the, for instance, even a deep field picture from Hubble, um, in this little bitty spot of sky, there's like thousands of the galaxies or whatever, and that's just one literally a little bitty like in my astronomy research class, the professor showed an image of a deep field image, and the size of the image on the sky was the eye of Abraham Lincoln on a penny. I was like, that's how big the section of the sky was. And it was still like galaxy after galaxy after galaxy. And when we look that far into the that deep into the sky, we're looking far into the past, and those galaxies have evolved however many years it took for us to see it. So we look, 100, what 14 uh, redshift into the past, but that's millions of years into the past. And humanity has evolved in just a few hundreds of thousands of years. So I mean, it's just probabilistically. I mean, there has to be alien life out there. Just probabilistically. I don't have any evidence to present to you on that, but just from a strictly scientific perspective, probabilistically, I mean, how can it not be life out there probabilistically, right? We know when we look at the universe on a large scale. Like, let me switch my background to my um, pillars of creation background, right? So this is a background. This is a rendering that I did myself in my astronomy research class, where we had to basically access some astronomical data and render the data. So I actually downloaded this data from one of the repositories. They have the astronomical data that anybody could really access. Just search, Hubble pictures, and it'll come up. Um, but this is one example. But I say that to say that you could take the data from, let's say, uh, I don't know, one of the galaxies that's, well, let's say an Andromeda galaxy, right? That has as many stars as this galaxy, right? And if you look farther, like you zoom out, you can see that there's a whole bunch of galaxies, and you can see a sort of differentiation. But I can't remember the exact name of the thing. But if you zoom far enough out, you will see what looks like this. It looks like a bunch of filaments. And everywhere you look in in the universe, it looks the same. And what this means, the word for this is isotropic and homogeneous. Like if you look far enough into the universe, everything looks the same. It looks the same. And we start to understand that the universe is the same on the large enough scale. So being that this is not a special place on a large enough scale, this would suggest that if you look at another part of the universe, life will be there as well. I know if I'm making this clear. This is stuff I'm learning now, so I'm still getting clear on this stuff myself. It's kind of like the way, let's look at it on a smaller scale. Like if I walk to the forest, I can probably find a pond. And if I get some water out that pond, I'll see a bunch of amoebas and stuff floating around. You know, we remember that from high school physics. You'll see a bunch of amoebas and different things. And if I go to another pond and I get some water, I'll also see some amoebas. Because a pond is just, you know, that's the nature of a pond. There's water, there's bacteria, there's stuff in it. This pond, which is our area of the universe, we now know that is no different than any other area of the universe if we look at a big enough scale. If I look at at the solar system scale, not every single part of the universe has a star. That's unique. But if I zoom out far enough, this area of the universe is the same as every other area. So I propose then that there's likely life throughout the universe, since the universe at a large enough scale is homogeneous throughout it. So hopefully that makes sense. But again, do I have, you know, I can't present an alien to you or anything like that, but that's how I think about it. But if it's really interesting to you, I would suggest you look into these authors. Um, Fire in the Sky by Travis Walton. He wrote a book, is a lot better than the movie. The movie is not based on the book. It uses some things from the book, but in the book, Travis Walton talks about what he saw, what he experienced. Uh, yes, I did. So what you can do, um, go to my site and go to my personal site, and I believe you can actually hear me go in detail about one of the. And actually, you can find it on this site. I'm pretty sure I uploaded some of my uh, talks describing that. But that was in like the year around the year 2000 to 2005 when I was really interested in that, which I still find it interesting. But at that time, I was very much interested in always looking and I was able to see some UFOs. So you know, search the channel. You'll see we actually gave a talk and actually showed some drawings and gave some illustrations and details. You can search the channel for that. And Catherine says she's seen a UFO as well. Awesome. If you look enough, you'll see it. And again, UFO means unidentified flying object, so I can't like prove that it's from an alien race or something. But I know that during that period of time when I was focused on it and meditating on it, that's around the time when I saw things. So, but there's people that say that there's beings visiting here and they're telepathic and they could read your intentions. That's a good one to read. Another one would be The Plumbing of Tan. I haven't read this full book, but you know, it really impressed me because this author he took a picture of a UFO, and he actually posted the picture online. The ones I was visiting him, he took a Polaroid picture of it. Raleigh Martin. So I would say look at one of these two books. Do I believe in time traveling? I'm not sure about that one. I haven't really looked into it too much. To me, I think anything is possible with enough scientific advancement. So, I mean, do I think time travel is possible? I believe that it is. I don't have any evidence to say it is or not. Do I believe that people are visiting us from the past or future? You know, I think that's possible. I mean, I think that's possible. You know, we know that now time, space, we can't view time and space as separate. We have to think of time, space. to properly, for instance, calculate the rotation of Mercury around the sun because it's being affected by gravity, the increased gravity, the increased curvature of space by being so close to the sun. We have to calculate, we have to take time and space into account, and we can move through space. So it seems reasonable to me that we can move through time as well. We can move through space. So chances are we might even move through time as well, but just might not be aware of it. So it seems like technologically we can get to that point. And mathematician says, but Newton evidence says that time is two-dimensional. You cannot go into the future unless you increase the speed. Or you have to keep in mind that our understanding is always limited, and is always limited to the extent that we can understand. So, for instance, at the time of Newton, he would not have been privy to the technology and things that even prompted Newton to think of the things that he thought of, right? I learned from my relativity professor that before Einstein came to his conclusions, there was something called the Riemann tensors, in which Riemann speculated that time and space can be connected, or at least that space can be bent. And Einstein took these tensors and he was able to build upon what he did. So something this professor said was that our understanding is always built upon what came before. That could be was related to the understanding when they say we're standing on the shoulders of giants. Because if Riemann, I mean, maybe Einstein would have figured out something else. I guess we'll never know. But the history of the fact is that Einstein found Riemann's tensors and built upon that to make Einstein's special relativity, right? And keep in mind that Einstein also built upon Newton because he knew that Newton's equations works on small scales. And whatever he calculated for larger scales, like for increased gravity or speeds approaching the speed of light, he knew those equations still had to give Newton's equations when applied to a smaller scale. So basically, what happens is you can take Newton's equations. I mean, you could take Einstein's equations and you could input slow speeds, and it will give you the same thing you get with Newton's equations. It'll be just slightly more accurate, but it will give you the same thing. But Newton didn't have Newton's equations because he invented these equations. So Newton would have been limited on what he could understand because he did not have Riemann's tensors. And he didn't have what he developed because he developed it. Einstein was able to develop that. So what I'm saying not to say is there's somebody who's going to come along in the future who will be able to take what Einstein did and take what Newton did and take what Riemann did and take what somebody else did who we're not even aware of now. They might not even be alive now. And that person will be able to take what all these people do, and then they will be able to see how we can, you know, go faster than C, or how we can breach the time space without going as fast as C. So again, those things are going to come in the future based upon what we're building now. So that means that you, the mathematician, you need to study up. You need to learn science and make sure you understand it, right? So that you can develop the next thing. Where if you don't develop time travel, you might help develop the thing that the next person does to develop time travel. So that's why we all need to start to really learn and start to understand science and start to see through all the pseudoscientists out there, whether it be flat earthers or geocentrists or whatever, and start to hold them to task to actually, instead of just being embroiled in this, gotcha stuff, actually have real world things that we can base our things on, like refrigerators and power plants, to show that these things work. And they continue to build upon that so we can go to the next science and then we can get to the next thing and we can do these things. Right? And Catherine says, only by looking at the stars, but I don't think we have the technology right now, or what it might do to us. Yeah. We were still building, right? We still building. Mathematician says people says Einstein. People say people says Einstein. God. Oh well, yeah. I believe that. I believe there are technology that we don't that's not revealed. But again, that's I think that's really on us because we didn't let them do that. If we didn't let people hide technology, if we didn't let the government lie to us, if we held them to task and said, "Hey, you promised this in your election, you didn't do it, you got to go." Or what's up with these secret dark projects? We're going to reveal this. Is Area 51 there? If we demanded this stuff and either ousted the people that are there, or if they didn't, if you know, if every single new person does the same thing, just dismantle the government altogether. Because again, the government is there to represent us, our liberty and freedoms. That's how America came along because we recognized that we're going to declare independence from Britain and make what we want. We could do that again if we wanted to. But we have to be willing to accept our liberty so that we want to say, okay, if you have technology that you're hiding from us that can free the world from dependence on fossil fuels, either we're going to find it or we're going to have to oust these people. You know, we could do that. So that's on us, right? That's how I think that is. There is something in the ocean. NASA moved from searching deep waters to exploring space. What do you think? I don't know. I don't really get into the conspiracy stuff. I would just think if you think that's the case, the mathematician, what are you doing to reveal that? Right? What are you doing to either develop the knowledge to build or develop a company that can explore the ocean and find that, or find the people who found it to reveal it? But you know, I don't put a lot of time into saying, oh, the government is hiding this or doing that anymore, because I start to realize that the people who say that, that's all they do. They just spend all their time saying, all this stuff is being hidden, but they don't do anything to either get it revealed or develop it so that we understand it. So, you know, I just don't really focus on that so much. You know, I don't really believe anybody's going to help me. Like if I went there to say, hey, we're going to figure out what's going on with Area 51, if all of us wanted to go there, then we could do that. But I don't think everybody's going to do that. Nobody really wants to believe it. Nobody really wants the truth that much. If they did, then we would do what it takes to get it. So I just don't really focus on that so much. But awesome. I'll go ahead and close up. Is at the bottom of the next hour. I'll be back next week. Good questions, math position. Thanks everybody for showing up. I'll see y'all then.